All right, we're going to take a look at the next part of electrochemistry, and it is called Redox Stoichiometry. So hopefully you all remember what stoichiometry is from either Chemistry 20 or our review unit, but essentially stoichiometry is used to predict or analyze the quantity of a chemical involved in a chemical reaction. So we're talking about quantitative reactions. So we assume that all reactions are spontaneous, fast, and stoichiometric or quantitative. All right. So redox stoichiometry, we're looking at the reaction of a titrant and a sample, and we have either a strong oxidizing or reducing agent involved. Now, in terms of redox stoichiometry, two common oxidizing agents used in titrations are dichromate ions and permanganate ions because they both undergo a color change when they are in a they have been either oxidized or reduced. So dichromate ions, okay, these guys go from an orange color to a green color, and they go from orange when they are the dichromate, so Cr2O7 2-, and they turn green as a chromium ion in solution. Now, permanganate ions change from purple, and it's kind of a purple-pink color, and they turn to colorless when they are oxidized. So again, this is purple as permanganate, and it turns colorless when it's manganese, and it's usually manganese 2 positive. So these are agents that undergo a color change, which is why we tend to use them in our redox stoichiometry. Now, in these stoichiometric reactions, we have the concentration of the titrant has to be known. So that is similar to any stoichiometry that we've dealt with in terms of solution stoichiometry in Chemistry 20. And we have to have a preparation of a standard. Now, the preparation of a standard is essentially creating a solution that has a very distinct known concentration. Now, generally, it's an entity that has a large molar mass in order to minimize the difference in what our mass changes when we create this standard solution, but that is very, very important. Now, sometimes in redox stoichiometry, we have to do 2 titrations, one to create our standard and get our appropriate concentration of our standard, as well as another one with whatever entity that we are testing. So that is very important to know as we go through. Now I'm going to go over an example. I'm going to have to pull up a separate, an additional page here to go through this, but let's just take a look. Now redox stoichiometry is usually done with some sort of titration. So we're talking about, in this question, potassium permanganate. All right, and again, that's KMnO4. And it cannot be directly prepared precisely with a known concentration because the permanganate ions react with organic and inorganic impurities in the water and the water itself. Thus, potassium permanganate is not used as a primary standard. So what we're going to do essentially in this sort of practice analysis is we're going to try and figure out our concentration of potassium permanganate using a primary standard. So our primary standard in this situation is our tin chloride. So we have a known concentration of tin chloride, and we are going to titrate potassium permanganate in order to calculate that concentration of potassium permanganate. Now, once we have this potassium permanganate concentration, we would then usually use the same solution of that potassium permanganate to calculate the concentration of a different entity or a different redox entity that would happen in a reaction. So let's just take a look at what we have here, and then we're going to go through how to solve this problem. All right, it says we have potassium permanganate we add it to acidic tin chloride, and we have a known concentration of this. The tin chloride solution is the primary standard. So that is what I put in the purple box here, is that it's the primary standard. Now, our trial number 1, we have an initial burette reading of 1 milliliter. And our final burette reading is 18.4, giving us the volume used in that first titration as 17.4. Now you'll notice by the color change, it says it's a dark pink color, and because it is a dark pink color, it means that we might have used more volume than we maybe expected there. We would want the color change to be the minimal color change that we'll see. So we don't want a dark pink, we would probably be aiming for a light pink color. So let's look at the remaining trials, 2, 3, and 4. When you look at the initial and final, when you subtract them all, we get 16.9, 16.7, and 16.8 milliliters, and we get a nice light pink color in all 3 trials. Now, I would say that when we're taking an average for this sort of experiment that we have going on here, our analysis here, I would rule out trial number 1. Trial number 1 has a data point that is sort of not effective for us. It was an outlier, and it was the first trial, which tells us that it was probably inaccurate a bit. So what I would say is that our average volume here used is going to be the average of 16.9, 16.7, and 16.8, which is 16.8 milliliters. Okay. So I'm just going to pull open a second page here to show you how we go about solving this problem here. So essentially, we use our 5-step method in order to figure out what we have in our solution, and then figuring out our strongest oxidizing agent and our strongest reducing agent. So it says we have potassium permanganate. So we have potassium permanganate. Now remember, it's an ionic compound, and ionic compounds dissociate when they're in solution. So we have potassium and permanganate ions. Okay, and it says we've titrated with acidic tin 2 chloride solution. So we have acidic, which means we have hydrogen ions present. We have a solution, which means we have liquid water. And we have tin chloride. Again, it is tin 2 and chloride ions. So we have all of our entities present in solution, which means that they ionize into their constituent parts. Now, when we take a look here, we need to start identifying what entities can be our SOA and our SRA in this equation. So we go back to our chemistry data booklet, and we're going to try and find which of these entities can be an OA and an RA, and we'll find which one is our SOA and our SRA. So let's take a look here. I'm just going to maximize this guy, and we're going to go jump over to our chemistry data booklet. Scroll down to page 7, and we'll start with potassium. We see that the potassium ion is here. All right, so we know that our potassium ion, can be an OA. We also see that tin 2 can be an OA. All right. However, I also see that tin 2 can be an RA, so that can be an OA or an RA. We know we have a liquid water, so we have liquid water here. Again, it can be an OA, and it can be an RA, wherever it might be. Why can't I find it? Oh, here we go. Okay, so we have water that can be an OA or an RA. We have tin that can be an OA or an RA. We have our hydrogen ions that are here. Again, they can be an OA. Combined with our permanganate and our hydrogen, okay, this can be an SOA, I would say, because it's pretty close to the top of our table here. All right, we also have chlorine ions, or chloride ions, and where do I see those? Okay, so here we see that chlorine ions, they can be an Ra. They're a fairly weak Ra. We also see that, where else can we find anything here? Oh, we also see that chlorine mixed with water here, that could be an Ra. Again, it's a weak reducing agent, so it's not a very good one. And what else do we see? That is about it. So when we look at our data booklet here, we see that our strongest oxidizing agent is this guy up here, so our permanganate and our hydrogen ions combined. And our strongest reducing agent is actually this tin 2 down here. It's the strongest one, it's the closest one to the bottom that we found. So if we remember our two half reactions, let's jump back to our page there and we'll start labeling our SOAs and our SRAs. So we have these two entities here that we can identify as our SOA. We also identified this as an RA, this as an RA or an OA. This was our SRA, can also be an OA. Chlorine with water was also an RA, but it was a weak reducing agent. So we see that our two half reactions that we're going to be dealing with is our first half reaction with our permanganate ions, so our MnO4- plus 8 hydrogens and 5 electrons gives us manganese ions and water molecules. Okay, and then we have our SRA, which in this case is our tin. So we have our tin 2. And remember, we read these from right to left when you're reading these. Okay, and this gives us tin 4 and 2 electrons. Okay, so there's our two half reactions that we are dealing with. Now, again, the most important part of electrochemistry when we're dealing with these types of reactions is balancing the number of electrons. Now, what you'll see is we have 2 electrons on our strongest reducing agent and 5 on our strongest oxidizing agent being transferred, so we have to ensure those are balanced. Okay, I do that by multiplying by a coefficient. And I would say this guy needs to be multiplied by 5, and this guy needs to be multiplied by 2, and I can get a net reaction. So when I do that, I would cancel out my electrons. I don't need to include them because they are balanced in both what is gained and lost. But I would write out that I have 2 MnO4 minus plus 16 hydrogens plus 5 tins. I have 2 manganese as a product. I have 8 water molecules, and I have 5 tin 4 ions. Okay, so the question that we are asking here is what is the concentration of our potassium permanganate? So what we know so far, and this is what we've done with our chemistry 20 as well, so this is consistent. We use our chemical reaction as sort of a table organizer to write down what we know for each entity. And so far, what we know is that in a 10 milliliter sample, which is in our question there, is that our volume is 10 milliliters. Okay, and our concentration of this guy was known, and the concentration was 0.05 moles per liter. So let's just double check that I have the right values here. So when we go back to our question, we see, oh, what's happening here? let's see here. We see on our question that we have a 0.5 mole per liter tin chloride solution and we have 10 mils of it. Okay, our average volume here is 16.8 milliliters, so let's go back to that question. Again, 10 milliliters and 0.05 mole per liter concentration. And my concentration of my permanganate is what I am looking for. And my volume of my permanganate, my average volume for my experiment, was 16.8 milliliters. Okay, so my first calculation that I need to do is to calculate the number of moles of my tin, in which I use a mole ratio to then calculate the concentration of my permanganate. So let's go through that first calculation. Okay, so we have the number of moles of our tin is going to equal the concentration times the volume. So N equals C times V. And when I do that, I get my moles is equal to 0.05 moles per liter multiplied by 10 milliliters. And because we have liters in our moles per liter unit, I'm going to convert that into my milliliters into liters. So I have 0.01 liters. So when I do that calculation, I get 5 times 10 to the negative 4 moles. All right, so now that I have the number of moles, I need to do a mole ratio in order to calculate the number of moles of permanganate that I have. So I have essentially 5 times 10 to the negative 4 moles, which in other words is 0.0005 moles, and I'm going to multiply that by a mole ratio. Now I always like to write down moles of what, so I know what I need to put in my mole ratio. So this is moles of tin. I'm going to multiply that by a ratio where I have tin on the bottom because I need to cancel out my tin units, and I'm looking to calculate my moles of permanganate ions. So in order to do that, my mole ratio is going to be a 2/5. Again, I get that from my balanced chemical reaction, which I had to get from my 2 half reactions. And when I do that, I get a chemical amount or number of moles to be 2 times 10 to the negative 4 moles. Okay, or 0.0002 moles. So once I've calculated the number of moles of my entity here, I can then use the number of moles in a calculation to calculate the concentration. So then I have concentration is equal to moles over my volume, and my concentration is going to be 2 times 10 to the negative 4 moles over my volume, which is 16.8 milliliters. Now again, I want this in moles per liter, so I'm going to convert this to liters. So it's going to be 0.0168 liters. And that's going to equal once I plug it into my calculator here, that's going to equal 0.0119 moles per liter. So when I go through these stoichiometric calculations, there's many steps involved, and you will see that you may need a full page or at least a half a page to solve some of these problems, because we actually have to start with our 5-step method at the top and using our 5-step method to calculate our 2 half reactions or to find our 2 half reactions from our strongest oxidizing agent, our strongest reducing agent. Balancing our number of electrons, again, is always one of the most important step, because we have to have the same number of electrons donated as we do accepted. And we come up with a net equation. This net equation, this balanced equation, is important to get a proper mole ratio. From there, you can calculate number of moles, and from number of moles, you do the mole ratio, And whatever you're looking to calculate, whether it be concentration or volume, you can use that mole ratio to plug those values into a new concentration formula to get your new concentration or volume, or whatever variable you're looking to solve for. Now, I think that's it for this lesson. There are a lot more examples that you can find online, and there's definitely going to be an assignment to follow to make sure that we're all on the same page with these types of calculations. So if you need to go back and rewind, do that now, and good luck.